Welcome back. Today we're going to talk about essential functions, section 2, chapter 1. Our first function is a linear function. Called linear because you plot the function, you expect a straight line as the result. And how does the function look like? F of x equals mx plus b, where m is the slope and 0 and b is the y-intercept. So what does it mean? Let's look at an example. For example, if you have f of x equals 2x plus 3. These coefficients could be positive or negative as well. Let me turn this to minus 2. Minus 2x plus 3. Could be decimal. It could be something like square root of 2. Doesn't really matter. Okay, just for simplicity, I'm going to pick an integer. This way it's easier. So this is a linear function. The degree of the variable x is 1. So the result would be a linear function. Slope would be negative 2. Y-intercept is the point 0 and 3. Yeah, I'll explain what the y-intercept is for those who've forgotten. So let's say if you wanted to graph this function, what would you do? Is you will find some x and y coordinate. Let's pick x equals 0, 1, and 2. Since it's a straight line, 2 points is just enough, but I'm going to pick 3 in case. If you pick 0, what do you get is 0 times negative 2 would be 0 plus 3. So you're calculating f of 0, which turns out to be 3. So you'll get the y value of 3. If you find out what is f of 1, you'll get 1, 1. F of 2 would be 2 times negative 2, negative 4, plus 3 would be negative 1. This would be negative 1. And now, you're going to graph this function. What you see is a couple of points. One of them is 0, 3. So here, let's say 1, 2, 3. This is the point 0, 3. Then you have 1 and 1, 1 and 1, and then 2 and negative 1, 2 and negative. And you can draw a straight line passing through those points. Why? I can never draw a straight line, by the way. This is, let's say, the straight line. Let's assume it goes through this point. What does it mean? It means any point that you pick on this straight line doesn't really matter where it is. It should satisfy this equation. So if I pick something like x equal to 3, what do I get for f of 3? It would be 2 times negative 3 plus 3, you will get negative 3. So it means at 3, your y value should be negative 3. That's the point. Negative 3. Okay. So what is the slope? The slope is rise over run, if you've forgotten that. So let me undo these too many dots. Okay. And what was rise over run? That means if you start from one point on the on this line and move, this slope is negative 2. You can write it as negative 2 over 1. This is rise over run. That means if you move along the y to negative 2 direction and then move along the x 1 direction, you'll end up with another point on the line. So here, which means move down, this is along the y, move down 2 units, negative 2 means 2 units, so this is negative 2 step. And I'll move 1 unit to the right. Where did I end up? At the next point. If I continue this procedure, move down 2 units, then 1 unit to the right, I'll end up at the next one, so on, 2 units. Doesn't really matter where you start. You can start from this point, you'll end up with another point on the line. So the slope is basically the amount of movement that you need to make in each direction to end up on the line again. So this is the slope. And y-intercept, what does the y-intercept tell you? It says, where do you cross the y-axis? The y-intercept is intersection of the graph with the y-axis. Where does it happen? At this specific location. What is the x-coordinate? Since you're on the y-axis, the x-coordinate must be always 0. That's why I pick 0. And what is the y-coordinate? 3. Where do we get that 3 is from here. And how do I know this is always the y-intercept? That means if you pick x equal to 0, this term always disappears. 2 times 0 is 0. Negative 2 times 0 is 0. So you'll get 3. So this is basically your y value. Okay. So if you're given linear function just by having the y-intercept and the slope, you can simply graph this function. So if you've forgotten that, just do a couple of examples. Linear function is one of the easiest ones. It's a specific case of polynomials, so I'm going to focus on polynomials mainly. And by the way, what is the domain of linear function? It should be all real numbers. I can pick any x value, replace it in the function, no problem. Polynomials is a more general case of linear. So instead of having only degree 1, you can have degree 3, degree 4, x to the power 5, and so on. The simple case of polynomial would be a linear function. Another one would be something like quadratic. You've seen different forms. So here, an x to the n, an minus 1 x to the n. Normally, this is the format that they write for polynomial. That means there's a coefficient in front of the variable x to some power. That coefficient is a related power. So we say linear, this is coefficient for x to the power n, coefficient for x to the power n minus 1, and so on. That's why this sub-index is n minus 1. So ai's, which are the coefficients, are real values, and they're all constant. Here's an example. X cubed minus 2x squared plus x plus square root of 5, for example. This is a linear polynomial. Doesn't really matter if the coefficients, it can have 2/3 here as a coefficient, it can have 1/7 coefficient. The coefficients do not need to be integers. They could be decimal values. I can have 0.1 here. As long as the coefficients are real values, I cannot put an I here. I cannot make it complex number. As long as the coefficients are real value, then it's a polynomial. So just make sure that the exponents are integers. And you don't need to always have all the exponents. This term, if this term wasn't there, still this is a polynomial. Has degree 3. Okay. Here, what we've learned about polynomial is we normally deal with second degree polynomial because we can solve that easy. Cubic is possible as well, but fourth degree and higher, there is actually a theorem that you cannot solve a general case for those. So here, what is the domain of the polynomial? All real numbers. Why is that? Because I can replace any x value and I get a corresponding y value, and I get exactly one corresponding. So here's an example. Let's say f of x is given. This is a very common example that we deal with. X squared minus x plus 6. It's a quadratic function, second degree polynomial. Sometimes they ask you to find out what is f of a constant like 0. What you get is 0 squared minus 0 plus 6 is simply 6. And sometimes they tell you find where f of x equals to 0. For what x value this happens. That means set the function equal to 0, is x squared minus x minus 6 plus 6 equal to 0. Instead of f of x, I replace 0. And you can factor this, you can use quadratic formula. In this case, I can factor it, x minus 2, x plus 3 equals 0. Therefore, x is either 2 or negative 3. So that means if you pick x equal to 2 or negative 3, the corresponding y value is 0. And how do they look like, the quadratic functions? Just by figuring out these 2 points, 2 and negative 3, I can say here's 2. At 2, y value is 0 because f of x becomes 0. So if f of x is 0 for x equal 2 and negative 3, it means y must be 0 at these 2 points. So you should have a point 2 and 0, and 3, negative 3 and 0. So at negative 3 as well, here negative 3. Okay, so these 2 points belong to the graph, and quadratic functions are parabolas. So do you expect something like this? You can figure out where the vertex is. Vertex is this end point down here. This is halfway between these two, between 2 and negative 3, which is happen to be at 1/2. You can find out the y value by simply calculating what is f of negative 1/2. And by the way, this middle point is a way to figure out what that is based on this coefficient. General case of a quadratic, f of x equals ax squared plus bx plus c. So that vertex is, the x value is negative b divided by 2a. B in this case is negative 1, so you get x equals b divided by 2a. There is, b divided by 2a. It's supposed to be negative b divided by 2a. Wait. Did I make a mistake at some point? Oh, sorry. This was x minus 3. Good. Now I figured out this mistake. This is x minus 3 and x plus 2. So this is positive 3 and negative 2. Here we go. I make mistakes as well. So here, let me fix this graph. Okay. If you caught that, that's a good indication that you know how to factor better than I do. Sometimes I make these mistakes. Just make sure that if you find a mistake, maybe write a comment. This way everybody else knows that there is a mistake involved. Maybe I can fix it. Okay, so here, 1, 2. Yeah, so at 3 we have a 0, at negative 2 and at positive 3 we have 0. Then the graph will look like this. The vertex happens to be at 1/2 actually. There we go. Now, if you look at the vertex form, the x coordinate is at negative b divided by 2a, which is negative 1 divided by 2 times 1. It's the same as the 1/2 that we got here. This is the x coordinate of a vertex. Always use this. Okay, I don't want to be very exact about all these topics. You should know most of them by now. If you want to find the y value, you can always calculate by finding what is the f of negative 1/2. Replace negative 1/2, positive 1/2. Replace positive 1/2 into the function, you will find the y value. Okay, generally the domain is what I'm going to talk about today. And for polynomial, the domain is all real numbers. Power functions are a specific case of polynomials if you pick the exponent as integer. So here, power function means f of x equals x to some power a. If I pick those powers to be integers, like 1, 2, 3, 4, so what do I get is f of x equals something like x squared. This is a quadratic function. Turns out to be the simplest one. If I pick only x, what is that? That's a linear function. I'll get this 45-degree angle line. If I pick it to be x cubed, then you'll get cubic function, which looks like that. So all these, if you pick the exponent to be integers, then you have a linear or quadratic or cubic and so forth degree polynomial. Domain for those guys would be all real numbers. But what if I pick the exponent to be something like a rational number, like a fraction? So let's say if I pick the exponent to be 1/2, for example, x to the power 1/2. If you remember, x to the power 1/2 is the same as square root of x. So now the domain is, in this case, is different. I cannot have negative number underneath the square root. So what would be the domain? Be all numbers greater than or equal to 0. This would be the domain, right? The 0 to positive infinity. What if I have f of x equals x to the power 1/3? This is a cube root. Domain for this one, all real numbers. Cube root, you can have positive or negative number underneath. There is no restriction. The only restriction happens when you have an even root. So something like f of x equals x to the power 1/6. This is the 6th root of x. Again, in this case, domain all numbers must be greater than or equal to 0. Because you cannot have negative number underneath those even roots. What if the fraction was something like x to the power 2/5? That means consider x to the power 1 over 5 and the square it. That's what it means. So x to the power 1 over 5 would be fifth root of x, and if I square it, it would be x squared. So this domain for this guy, all real numbers. Again, fifth root, no problem. So general case, if I have a fraction, f of x equal x to the power k m over n, let's say, m over n. This means x to the power m, nth root of that. So you guys remember this probably, maybe not for general case, but at least for x to the power 1/2. The general is nothing different. It's just the extension of it. What if the exponent was negative? What if it was x to the power -1? This means 1 over x to the power +1. You can flip it and make it a positive exponent. What if it was f of x equals x to the power -2? Then this would be 1 divided by x to the power 2. If it was x to the power -3, and so on. So what is the domain in these cases? The domain would be you're not allowed to have 0 in the denominator since they are fractions. So x cannot be 0. X cannot be 0 in either case. If I combine this with the fraction and say x to the power, let's say -1/2, then this means 1 divided by x to the power 1/2. X to the power 1/2 means square root. That means now if I want to talk about the domain, these are the domain. If I want to talk about the domain, it means the domain, you cannot have 0 because it makes the denominator 0. Neither you can have negative number because underneath the square root would be impossible to have negative number unless you deal with complex values. So here I will say the domain is everything greater than or equal to 0, but 0 is not accepted. So I erase that equality. If it's 0, then you have 1 divided by 0, which is undefined. This is the only difference that happens. Generally, it's a combination of fraction and square roots that makes it harder a bit. If you have each one of them, or they're separately, if you're dealing with fraction, it's only checking the denominator. If you're dealing with square root, then you set an inequality. You want to have positive values underneath the square root. Okay, by the way, these domains, these two x not equal to 0, you can write as all real numbers except 0. Or you can write as -infinity to 0, union 0 and infinity. I talked about this already yesterday, but in the last lecture, you can go through that as well. Okay, so these are examples of power functions. We have rational functions as well. What is the rational function? Rational function is the fractions, but the only difference is that for fraction, for specific rational functions, the numerator and denominator are both polynomials. So you have a polynomial divided by another polynomial. They don't need to be the same degree. The numerator could be a constant, the denominator could be a variable. Cubic, for example, polynomial. Here is an example. Let's say you have 2x minus 1 divided by x squared minus 5. This is a linear function divided by a quadratic function. Example, f of x equal to that. By the way, I always use f of x. What if I use g of x? So this way, you do not expect always the same functions. What if I ask you what is the domain here? Again, we've talked about this. You say, dealing with fraction means I do not need to have 0 in the denominator. So figure out where the denominator is 0 and exclude those points. X squared minus 5 equal to 0. X squared equals 5. X equals square root of 5. Take a square root and use plus or minus. So the domain is all real numbers except positive or negative square root of 5. As an interval, you can write this as -infinity to -√5, union -√5 and 5 root 5, union √5 and infinity. And again, you can do this interval notation by simply drawing the number line, saying here is -√5, here is √5. Do not need to write it in decimal. Use the exact form. and say I'll exclude these 2 points. Everywhere else is okay. But I accept this section, I accept this section, I'll accept this section. I exclude these 2 points, negative infinity to negative root 5, and so on, these areas. Rational functions are not too complicated. There is the algebraic function, which is a combination of both rational functions, polynomials, power functions, square roots, everything combined together. What we call it is an algebraic function. That means it's a combination of addition, multiplication, all those operations added together. Let me move this up a bit. The algebraic function, I wrote an example earlier just to discuss it. If they ask you, you see, do you have fractions, numerator and denominator is square root, you have dealing with cube root. If I ask you separately to find the domain of this function for each part, you look at this and say, okay, I want to figure out the domain of that, and I want to figure out the domain of this one. I'll take their intersection, whatever they have in common. Domain of this one, this is cubic, all real numbers. So there is nothing to be worried about for this term. The other term for this one, for the fraction, you don't want to have 0 in the denominator, neither do you want to have a negative number underneath the square root. So what do I want? I want all x's to be greater than or equal to 0, but I don't want the denominator to be 0 either. So I'll erase this 0 in the denominator. I can change this to x plus 1, ask you, okay, now what happens to the domain in this case? You say the same thing. Underneath the square root must be greater than 1. It could not be 0, otherwise the denominator becomes 0. Then you say x must be greater than negative 1, and as a domain, this is from negative 1 to positive infinity. If you break it up into separate pieces, easier to do that. If you find 2 different domains, let's say this was square root as well, square root of x plus 7. And you solve this and say, okay, the domain for this one would be x plus 7. Let me change this to negative x plus 7, just to make it a bit more complicated. Negative x plus 7. Okay. Negative x plus 7 greater than or equal to 0, because I do not want to have a negative number underneath the square root. So what is that? It is x is less than, okay, let me do this step by step. If some of you have forgotten, when you multiply a negative, you should flip the sign, so x is less than or equal to 7. The domain now is a combination of these 2. I should satisfy both of these 2. How do I find the domain in that case? Draw the number line. Find each one separately. I'm going to use the blue color for this domain and the red one for this one. Okay, so here x less than or equal to 7. Here's 7. Less than or equal to 7 means 7 is acceptable because I have the equality, everything below as well. This is for the result of this inequality. The other inequality, x greater than negative 1, here's negative 1. Negative 1 is not acceptable because there is no equality, so open circle. X greater than negative 1, everything in this area. What is the common section? Here's the common section. This is what you care about. So what is the domain? The domain simply becomes from negative 1 parentheses, because it's not acceptable, to 7 bracket. But if you have multiple terms, you can find the domain of each one separately, then take an intersection. Just to refresh your memory on those. Okay, trigonometric function. This is kind of a subject that you should know either from trigonometry or from pre-calculus. We've seen sine, cosine, tangent functions. You don't want all those information. I don't want you to remember all those information, but the basic parts you should know. You should know that the sine and cosine are always between 1 and negative 1. You should remember that the sine had this graph. Cosine on the other side would start from 1, decrease, something like this, over the period from 0 to 2 pi. That would the whole look like. Just to refresh your memory a bit on the sine and cosines, this way, graphing it. not accurate, but let's say something like this. Supposed to be at the same location here. This is pi half, pi, 3 pi half, and 2 pi. Okay, so just make sure that you look at sine and cosine function, tangent function if possible. It's a combination of sine and cosine. So for example, if you're given this function involves sine function and they ask you find the domain, because later on when we talk about limits and derivatives, you'll deal with trigonometric functions as well. So what do we say? We say the denominator cannot be 0. So 1 minus sine x equal to 0, and I want to exclude the result of this equality. So what do you get? You get sine x equals to 1. Where do I get sine equal to 1? You remember the unit circle? Where do we have sine equal to 1? It happens to be at pi half. If you remember the graph, this is the location, and it happens to be at pi half. So I'll say x equals to pi half. And since sine is a periodic function for every 2 pi plus 2 pi n, 2n pi, you can write it. N is an integer, belongs to z. Okay, maybe you should write it as n equals 0 plus or minus 1, and so on. So what is the domain? Domain is all real numbers except pi half plus 2n pi. Okay. Make sure that you refresh your memory on trigonometric functions. They're very useful for our work. Okay. Exponential and log function. This is another one that we're going to talk about mostly throughout the work, throughout the definitions of derivatives, antiderivatives, and all those. So make sure that you look over these stuff. Specifically, exponential look like a to the power x. Difference between exponential and power function is for power function you have x to the power a. The exponent that is constant. For exponential, it is the base is constant and the exponent is a variable. For example, f of x equal to 2 to the power x. This is an exponential. E to the power x. E was a constant like pi, if you forgot. On the other side, log is an inverse function for the exponential. So you have the base fixed, something like ln x. That was an exponent, a log function with the base of e. The bases of exponential and log are always positive. They will never pick 1 because it would be constant value. So here maybe is an example. Let's look at 2 to the power x. F of x equal to the power x. And they ask you to graph this function. Then I can talk about the domain. So graph. Draw this table. X, Y, I'll pick some x values, -1, 0, 1, 2, for example. Find the corresponding y. If you replace -1, 2 to the power -1, we talked about negative exponent, it's the same as 1 divided by 2 to the power 1, so 1/2. This is 1/2. If you replace 0, 2 to the power 0, this is very important. It's never 0. 2 to the power 0 is 1. X to the power 0 equals 1 as long as x is not 0. So this is 1, 2 to the power 1, 2 to the power 2 would be 4, and so on. You can continue. 2 to the power 3 becomes 8. So how does the graph look like? Pick a different color. Okay, so I'll have -1 and 1/2. -1, 1/2. You will have 0 and 1. Here's 0 and 1. 1 and 2. 2 and 4. Somewhere. Okay, so the graph would look like something like this. Going through all these points. Here's the important part. You never cross the y-axis. Doesn't really matter what value of x you pick. If I pick -10, what you get is 2 to the power -10, which is 1 divided by 2 to the power 10. It would be 1 divided by 1024. Still a positive value. Very small. It'd be something close to 0.0009, whatever. It's still very small, but it's never zero. Okay, it's never negative and neither zero. So it's always above the x-axis. So what can I say about the domain? Remember the projection? If you project this onto the x-axis, you will cover all the x-axis. So the domain for the exponential, domain is all real numbers for the exponential. On the other side, let me write it. Domain of exponential, all real numbers, and the range, which is the important part. All the y values, if you project, you only cover the y-axis. On the y-axis, what you get is only the top part of the y-axis. So if you project this, you'll cover only this section. The graph will never go below the origin, so you will have 0 to positive infinity. 0 is never covered either because the graph never touches the x-axis. So domain and range for the exponential will be this way. How about the log function? If they ask you to graph, do this here. Graph log x base 2, y equal to that. The relation between exponential and log, they're inverses of each other, which means if you have x and y, if I pick the y values, 1/2, 1, 2, and 4, if I pick exactly those y values, what do I expect for the y value is exactly the x values. So log 1/2 base 2 is simply -1. It will be this number. If you pick that input, you will get -1. Log 1 base 2 is 0, because 2 to the power 0 equals 1, therefore log 1 base 2 must be 0. 2 to the power -1 becomes 1/2, therefore log 1/2 base 2 is -1. So this would be 0, 1, and 2. So what happens to the graph? Here's the important part of it, is that if you're dealing with inverse functions, this is always true. The graph of f and the inverse of it are always symmetric about that 45-degree angle line. The graph will look like something like that. If I reflect it, I'll get this. This is the graph for log x base 2. And what you see is now the domain for the log function is only the right-hand side, but the range becomes all this y-axis. The domain of log is 0 to infinity, and the range of that would be, maybe I should say log x base a. The range would be all real numbers. Make sure that you review these a bit, because it's necessary to know how to calculate log values. Here's one thing that you should know, that if log x base a equal to y, means a to the power y equals to a. This is the relation between exponential and log. Converting between log to exponential and exponential to log. These tables satisfy this relation. Okay, I'm gonna stop at this point. This would be the essential functions that are basically necessary for this class. Make sure that you review all these functions, do a couple of examples of each, figure out if you can find the domains or not. It's very important that you always know how to find the domain, because without that, sometimes some solutions are not acceptable since they're not in the domain. Okay, let's stop here.